is to do this identification of lithology, porosity, and fluid saturation. We actually used to take our logs and go to software. Now, in this lecture, we don't want to use any softwares. We need to build our own skills on by looking with our bare eyes how we can identify lithology, how can we identify porosity, and how can we identify which model we need to use for fluid saturation. So that will be bare eyes, not really using any software whatsoever. You need to build your skills. When you look at the log, you say, this is a limestone zone, this is a sandstone zone, this is the dolomite, this is a mix of both. So that's the whole goal of this presentation, okay? So as I said, it's gonna be bare eye, lithology, porosity, and fluid saturation. No softwares, it's building our own technical and all engineering skills of how to identify these things by looking at the log without any external help. Okay? So the goal is identify lithology by bare eye, examination of through the examination of logging data, no software. Okay? So what's really lithology? What we mean how can I identify clays? How can we identify sandstone zones? How can we identify limestone zones? How can we identify dolomite zones? So these are the major three different lithology that we handle on daily basis in our reservoir. Clay is not a reservoir, but we need to identify clay. We need also to, by observation, identify the clay volume, because that will help us in saturation. We need to look at the log and say, oh, this is a sandstone zone, this is a limestone zone, this is a dolomite zone. We need to build these skills because these are more important than just going to the software. In the software, if you are not even skilled, if your eyes are not skilled in the way of evaluation, the software may fool you. Sometimes we take things for granted. We go to the software, we use the parameters that's already defaulted in the software, and it comes up with absolutely nonsense analysis, and somehow we believe the software more than what we believe ourselves. Then determination of porosity independent of lithology. Okay, I need to find out how can I get lithology without the effect of porosity, without the effect of lithology. This is very, very critical. Now, by looking at the log, I can say this zone is a limestone zone with 15 PU. This zone is a dolomite zone with 10 PU, and so on. So we need to build this as a skill by our eyes. Also decide on the proper fluid saturation. Which saturation model I need to use here in this zone, which saturation model will give me the best results, which saturation model will give me the highest error. So that's a very important skill. It also to build if you are a good reservoir characterization engineer. So what's required to do this? Okay, what are the tools that are required and what are the logs that are required? Actually, there's a minimum log. So for lithology, porosity, and fluid saturation, there is a minimum logging suite required. Call it the triple combo. Okay? So the triple combo is the minimum. That's why in every well we drill, we acquire the minimum of triple combo. Okay, there are so many other logging that are advanced. Sometimes we use them, sometimes we don't. But you will never see any well that does not have a minimum of triple combo. Sometimes some companies go with less than this, but that's after really doing 100 wells or 50 wells. When we really understand the reservoir, then we cut on costs somehow because the reservoir production is declining. We don't want to spend more money on logging, but that happens after you are very comfortable with your understanding of your reservoir. But the basic logging that we usually do is the triple combo. Then what is the triple combo? The triple combo is a group of 4 logs: gamma ray, neutron, density, resistivity. And we answered that question before. If we look at these number of logging tools, there are 4. So why you are calling it triple? Triple is 3. So why we call gamma ray, neutron, density as triple? Well, normally, guys, we don't count gamma ray as a tool. Gamma ray, we call it is a must-have. Gamma ray is a correlation tool. Gamma ray is not really a tool that we use or we count as a gamma ray part of the suite, okay? So the suite is neutron, density, and resistivity. So the gamma ray, if you go for cased hole, you go with gamma ray. If you're going to go perforation, you go with gamma ray. If you're going to put a plug, you go with gamma ray. So gamma ray is a must-have in every operation we do in any well. So that's why we don't really count the gamma ray as part of the suite. So the triple combo is neutron, density, resistivity. I'm very sure you also heard something about the quad combo. Quad combo, if you add to this the sonic tool, you call it quad combo. Then again, it will be 5. Quad is 4. Then if you remove the gamma ray, then the quad is neutron, density, resistivity, and sonic. Okay? So gamma ray is not counted as part of the combo. Yeah. All right. Okay. Perform the analysis for all wells. So you do well by well first. Then you start looking at the field-wide, how my lithology, how my reservoir is deposited, what is the connectivity between layers, is there a fault here, fault there. We talked about this last time, but today we need to look at how we identify this lithology, as I said, by our bare eyes. Then build the cross-section, as we discussed in lecture 1. So after you do every well analysis, you look at the porosity, lithology, and saturation, then you start building your understanding of the total field. So you understand every single well first, then you go for total field. There are some statistics that we do. We'll cover this in the next lecture, how we look at the statistical variation across our reservoirs. Okay? So let me start with lithology. Okay? Lithology actually requires gamma ray, neutron, and density. So the minimum thing to look at lithology is the gamma ray, neutron, and density. By looking at the gamma ray, looking at the neutron, looking at the density, I have to build my skills of how to look at these logs, and I say this zone is this lithology, this zone is that lithology, and so on. Okay? So gamma ray, neutron, density, if we look at the gamma ray, neutron, density on any log, here's what you see. You see that the gamma ray is in the first track with the caliper. Caliper is required because it actually gives me some comfort zone of how good my well will be, and also if I need to do any environmental corrections on the logging. We're not gonna go through the environmental corrections, but actually before you do your analysis of lithology or anything, you need to make sure that your logs are environmentally corrected because of some of the washouts, some of the mud weight, additives to mud weight. So many things that require environmental correction. So the assumption in this presentation is your logs are environmentally corrected, and now we have the logs ready for interpretation. So I can see the first track contains the gamma ray and the caliper. We have some scales that were given to us by the API. I will keep saying the API in this lecture so many times. But API has a big role of how we identify lithology. To some extent, that doesn't make sense sometimes, but we'll prove it to you that the API was very smart. And they requested all of us to follow. So the first track has the gamma ray scale from 0 to 300 here. I can say 0 to 300 is different than the API. Well, if you do your analysis, don't abide by the API. If you do your analysis, don't abide by the API rules. Once you're done with your analysis, then when you print logs for people to look at, then you abide yourself with the API rules. Okay? So from 0 to 300, just to capture the variation, the high variation of my gamma ray. On the second track, I have the neutron and the density. Okay? Neutron has a certain scale and the density has a certain scale. Let's just see what the API is telling us in this case. Neutron and density are on limestone scale. That will raise a huge question. What if my lithology is not limestone? How can I put my rock, which I'm very sure it's sandstone, how can I put this on limestone? How come the API is forcing me to go and use the limestone scale? Okay? And that's the whole thing about this presentation. We really need to understand the thinking that the API used to help us identify lithology by forcing us to go for limestone scale. Okay? Everybody understand that? The forcing of the API to go for limestone scale is a very helpful thing. I will prove this through the presentation. So let's just take what the API is telling us for now. Neutron and density are on limestone scale. Well, I understand the neutron will be on limestone scale. If I look at the scale of the neutron, it will be from 0.45 to negative 15, or from 45 to negative 15. We talked about the negative 15, and we had a lot of discussions on the negative 15. I think I also advise many of you guys to go and watch the formation evaluation lecture that we did before on biopetro. So actually, if still did not attend this one, I need to understand what is the negative 15 all about. You need to go back and watch this video. Okay. But for the time being, we'll assume that we all understand why the API put it from negative 15 to 45. So the neutron is on limestone scale, and the scale is from negative 15 to 45. Density also on limestone scale, and the scale is 2.95 to 1.9. So now we tell me, what do you mean density on limestone scale? Density is density. Why should I put it on limestone scale? What do you mean by putting this on limestone scale? Well, we talked about something about the density, that we use the density to calculate what we call density porosity. Density porosity, by definition, we prove this also in the formation evaluation video, that the density porosity is raw bulk that you measure from the density tool minus raw matrix divided by raw fluid minus raw matrix. Now here is a raw matrix. Since your neutron is on limestone scale, then your density matrix has to be also limestone. You cannot put one on the same track. You cannot put one log on a limestone scale and the other log on a different scale. That's inconsistency. That will actually make things very, very confusing. So for the scale to be from 2.95 to 1.95, you have to use raw matrix as limestone matrix. What is the density of the limestone? Is 2.71 gram per cc. This means that your density porosity, you have no choice for the raw matrix. But the density porosity is raw bulk minus 2.71 divided by raw fluid, which is the water, minus 2.71. Why you are using the water? Because that's the calibration fluid. The tools are calibrated to water, and that's why you need to stick with the calibration fluid. So we have feed density porosity is raw bulk minus 2.71 divided by 1 minus 2.71. So please, when you calculate density porosity, don't go and look for what is the lithology of this zone. No, don't do that. And I'll prove this to you in a few minutes. Don't do that. You have to use 2.71 because you plotted the neutron and the density on the same scale. I'm sorry, on the same track. Once they are on the same track, then they have to be on the same scale as well. I cannot put on the same track two different scales. One on a limestone scale and the second on a sandstone scale, and then interpret both. It doesn't work this way. Okay? That's why we isolated the gamma ray on one track by its own, because there is nothing called limestone, sandstone, or dolomite for the gamma ray. So gamma ray has nothing to do with this. That's why it's isolated in one track. But the neutron and the density have a lot to do with the lithology, and that's why they are combined in one track. And for consistency, you have to fix the scale. So if the scale is limestone scale, both they have to be on limestone scale. Are we all agree in this? Okay. The question will be, this is wrong. Yes, we understand this is wrong. My rock is sandstone. How can you force me to put it on limestone? Yes, we understand that. But if you bear with me a little bit, you will actually understand why we are doing this. Okay. So this are the same. This is the question that I just raised. Why putting my sandstone formation on limestone scale? Isn't this a wrong approach? Also, the guy who has dolomite will ask the same thing. Why putting my dolomite formation on limestone scale? I know it's a dolomite. But the question is, please, the answer is absolutely no. That's not a wrong approach. And we will prove this in a second. That's actually an advantage. Okay? How this will be an advantage, that's what we'll be discussing for this. And let's understand this very, very clearly now. So I put in front of you all the questions that can come up in your mind. By the API forcing us for a certain scale, that doesn't make any sense. Okay? My reservoir is not limestone. Why you're forcing me to put my logs on limestone scale? That's not right. No, actually it is right, and we'll show you how come this actually be right. Okay? So let's understand logs on the limestone scale. One skill that you guys need to build as characterization engineers is how to predict the log response before you even put the tools in the wellbore. Okay? A good characterization engineer can predict what the log should read before the tool goes into the wellbore. You need to build that skill. Okay? So let's assume that you drill the well. Here is your well that you drill. Okay? Now, you actually went to the zone of interest. Say, this is your reservoir. So I drill the well and I reach my reservoir. Now, from the cuttings, from the mud logging, when you look at the cuttings coming out of the wellbore at the shale shaker, if you guys went to the rigs or not, the shale shaker that the cuttings come out, and there is some mud engineers or mud logging engineers. They actually take some samples and they look at it under the microscope and they describe what type of lithology they have. They came to us saying, here is your reservoir structure. You have clay, you have sand, you have lime, and you have dolomite. Man, I have all of them in the same reservoir. Okay, I'm trying to make it interesting to see how things will actually vary and how can we identify this by using only the limestone scale. Okay, so I have clay on the top, I have sand, and I have lime, and I have dolomite. And let's assume for simplicity that all these sand, lime, and dolomite have the same porosity. Let's assume that all of them have 20% porosity. So I have these layers of different lithology, but they have the same porosity just for the simplicity of it. That goes to any other lithology, but let's just stick on all of them, they have 20p. So, and when I put the neutron, this one will have 20 pu. I'm not really sure what the neutron tool will be reading on the limestone scale. And this is how it's going to be on the limestone scale, and this is how it's going to be on the limestone scale. The density tool also was run, and it was reading 2.32 in front of the sand. Okay, and it's reading 2.368 in front of the lime, which is good. This is the density of 20% limestone. And is reading 2.496 grams per cc for the dolomite section. So I have 20 pu for each, but the density is different because sand density is different, the lime density is different than dolomite density. So I have actually these expectations from the value of the porosity and the value of the density. Okay? So now I know I have sand, lime, dolomite, they all have 20 pu just for simplicity. And I have also the density of each layer. Now, as a characterization engineer, what is my prediction of what the tool actually will read? Okay, so I will actually have predictions for gamma ray and neutron density because I actually went with gamma ray neutron density for lithology. So what will my gamma ray will read? Okay, first, since this is a clay zone, gamma ray will read high gamma ray. Okay. Since this is sand reservoir with 20 pu, here is another reservoir, here is a third reservoir. They are different in lithology, but they are my reservoir. They have 20 pu sand, 20 pu lime, 20 pu dolomite. Then my expectation for the gamma ray is the gamma ray will read high in front of my clay, and it will read low in front of my reservoir. Because if my reservoir contains a lot of clay, it's not really a good reservoir. So our expectation for the gamma ray is going to be from 0 to 150 based on the API scale, and it will take that shape. So gamma ray will read high in front of the clay zone, and it will read low in front of my reservoir. Nobody will disagree with this, okay? So that's my expectation for the gamma ray before I put the gamma ray in there, okay? Now, the role is of the neutron density, how the neutron density will read, okay? First, we'll say this is the gamma ray zone. Then let's just see how the neutron will read the 20 pu limestone, 20 pu sandstone, and 20 pu dolomite. Okay. Actually, I'm not sure if you studied this or not. There is actually the three scales. The limestone scale right in the middle. They call it calcite or limestone. Here is the quartz or the sandstone, and here is the dolomite. You can predict what the tool will read for each lithology on limestone scale. What do I mean by this? Let's just take it one by one. What's my sand porosity? My sand porosity is 20 pu. Where is my sandstone here? Here is the line of the sandstone. Everybody see that? Here is my quartz or sandstone line. Where is my 20 PU on the sandstone line? Here is my 20 PU on the sandstone line. Everybody understand that? So now my rock is sandstone and my porosity is 20, but that's 20 on sandstone scale. What is this 20 will be on limestone scale, because the API is forcing me to put everything on limestone scale. So all you need to do is to actually send an arrow from this point all the way to the limestone and read it. So I will take an arrow here and I will read this. This is 15, 16 and a half. So the 20 PU on sandstone scale will be 16 and a half on limestone scale. So this means that you're actually not reading the proper porosity on the limestone scale. Yes, we are not reading the proper porosity on the limestone scale. If it is sandstone, I'm reading less than it should. My porosity, I know it's 20 PU. Everybody follow me to the end, because this is very important to understand. Okay? So when my 20 PU on sandstone will read lower porosity on limestone. It will read 16 and a half. Okay, so this one will read 16 and a half PU. I know that for a fact. Okay, now we can ask, are you comfortable with this? Yes, I am comfortable with this, and I'll prove you that's correct. Okay, but just bear with us, and we will follow the rules of the API. I know it's my porosity of the sandstone is 20. I projected my sandstone porosity on the limestone scale, and it's 16.5. Now, what's the second layer? It's limestone. Okay, limestone 20 PU is here. Here is the 20 PU. Do I need to do any projection? No, it's limestone and limestone. Limestone and limestone will be on the limestone scale. So this one will be reading 20 PU. So the only one that it will read correct is the limestone on limestone scale. There is no difference. Okay. Let's just go for the dolomite. Dolomite is reading 20. Where is the 20 of the dolomite? Here is the 20 of the dolomite. Okay. How much 20 of dolomite will read on limestone? Again, you go and project your 20 on the limestone. Now, here is 25, 26, 27 and a half. So the 20 on dolomite will be higher than 20. It will be 27.5 PU. Everybody understand that? So we know that your porosity will read incorrectly if you put them on limestone scale. Question, are you still comfortable with this? Yes, I am still comfortable with this, because I will show you the value of this later. Okay, so we put everything on limestone scale. Everything will be consistently on limestone scale. No other scales. Even if we are 100% sure that your rock is not limestone. Okay, so I will take my now reading 16.5. So the 20 PU limestone, sandstone, it will be 16.5 on limestone. The 20 PU limestone, it will be 20 PU on limestone scale. The 20 PU dolomite, it will be 27.5 PU on limestone scale. Now we'll go back here and try to draw the neutron. Let's just plot the neutron. Neutron goes from 0.45 to 0.15. I know that my porosity is 20%, but because I put all the logs on limestone scale, what happened is that my sand is reading less than 20. So where my sand will be? My sand will be in this area, okay? Because this is 0.2 to negative 15. This is less than 20 PU. So my sand will show up here. And my dolomite will show on the higher one. So if I draw the neutron, it will be this way. 16 for the neutron for the sand, and 20 for the lime, and 27.5. So that's why I'm putting the neutron on this side, because it's less than 20. The lime will be actually 20, and the dolomite will be higher than 20. This is the higher zone than 20, and this is the lower zone than 20. Then the log will take the shape. So then I can actually draw what the neutron tool will read Once I know what do I have, okay? So that's if I now log my neutron, that's the neutron curve that I will see. It will read less porosity in front of the sand because I'm putting my sand on limestone scale. And we just saw that if I put my 20 PU sand on limestone scale, it became 16.5. When I put my 20 PU dolomite on limestone scale, it became higher, 27.5. The only one that stayed 20 is limestone on limestone. That makes a lot of sense. Okay, so that's why in front of the lime, I'm actually matching the 20. But in front of the sand, I'm reading less. In front of the dolomite, I'm reading high. Very simple. Okay, so I'm expecting that's the way my neutron will react. Okay, so that's why I'm saying build your skills before even you look at the data, before even you put the tools in the wellbore. I'm expecting what my reservoir is supposed to look like. Okay, now how about the gamma? How about the clay? How the clay you will read? Let's just go and review the clay a little bit. Okay, so what is the clay reading? Okay, let's go and review the clay. If you remember, we actually talked about the clay in the formation evaluation one. And if you look at the clays, what does the neutron tool read? The neutron tool reads how much hydrogen you have in dark. Okay, if you look at all the clays, do they have hydrogen? Actually, they have a lot of hydrogen. This one has hydrogen. This one has hydrogen. This one has hydrogen. All the clays, they have hydrogen from the water of the clay. This means hydrogen is too high here. Here is 8 atoms of hydrogen. Here is 4 plus 8 is 12 atoms of hydrogen. Here is 8 atoms of, so the too much hydrogen. When you have too much hydrogen, you have very high porosity. So your expectation is that in front of the gamma ray, I will read very high porosity. How high it is, I don't really care. Why I don't really care? Because it's clay, it's not a reservoir. It reads whatever it reads. I'm not really, I know it will read high, but I'm not really interested in how much it reads. Is it a reservoir for you? Does it do you really care if it reads 40 or 50 or even 60? It doesn't matter. Why? Because I will never perforate the zone. It's not on my interest. My interest is my reservoir. But I'm predicting that in front of high gamma ray, I have to see high porosity. The reason is all clays have hydrogen. The neutron tool measures hydrogen. When it sees high hydrogen, it will give you high porosity, as simple as such. That's why it will give you very high porosity here. Whatever the value is, depends on what type of clay do you have in your reservoir. Okay, so now I understood what my tool or how my tool will react in this sequence of layers between clay, sand, lime, and dolomite. Okay, all right. So let's continue. Now we predicted the gamma ray, we predicted the neutron. We need to predict the density. Okay, the density porosity. Okay, we understood. Density porosity has to be on limestone scale. You cannot do anything other than limestone scale by the API rule. Okay, so what is the density porosity? We put the density porosity in this format, and we said that the raw matrix has to be 2.71 because it's a limestone scale. Then my density has to be raw bulk minus 2.71 divided by 1 minus 2.71. Okay, and that's my density, and never ever forget this. Don't use any other lithology, the density of other lithology other than the limestone. It's a mistake. Okay, okay. We'll prove this to you in a second. Okay, all right. Let's just follow the rules here. The rule is your density porosity is raw bulk minus 2.71 divided by 1 minus 2.71. Let's just calculate the density porosity for the sand. What is the density of your sand? 2.32. Then I will take the raw bulk and I put 2.32 instead. Then I calculate my feed density. Okay? How about the density of the density porosity of my lime? The density of the lime is 2.368. Then I will change the raw bulk to 2.368 and I calculate my density porosity on limestone scale. How about the density porosity of dolomite? The density of the dolomite is 2.496. I'll go there, 2.496, put it in this equation, calculate the density first. If you do this, here is the feed density of the neutron, of the density in the sand. It will be 22.5. So if you put 2.32 here and you do the math, it will give you 22.5 PU. Is it still less than 20 or it's higher than 20? It's higher than 20. Just pay attention to this. The neutron, the porosity on the neutron tool is reading low, but the density porosity is reading higher than the 20. Keep this in your mind. So the density porosity reading higher than the 20. If I do the same for that sand, for that line, 2.388, it will give me exactly 20. Why? Limestone on limestone. It's very, very simple. It has to give you exact 20. How about the dolomite? The dolomite, I put 2.496. Then you do the math, then the density porosity will be 12.5. Is it reading higher or lower? It's reading lower. Okay, everybody understand that? So you take the density porosity, you put the density of the sand, you calculate the density porosity of the sand. You put the density of the lime, you calculate the density porosity of the lime. You put the density of the dolomite, you calculate the density porosity of the dolomite, all of them on limestone scale. This one became 22.5. So where should be? Should be in this section or in that section? It's higher than 22 or lower? It's higher than 22, should be in this section. How about the 20? It will be exactly over the 20. How about this one? It's less than 20, so it should be in that section. So the density porosity here, for the sand, it will be higher. It will be in this zone, 22.5. For the lime, it will be over it, 20 PU. For the dolomite, it will be less, so it will be in this. Then if you draw the density, what will happen? If I draw the density will be in this shape. Everybody understand that? Now we came up to a very important thing. And keep this in your mind, never ever forget it. Okay? Okay. So look at this. When I see the separation here, here is the separation between neutron and density. When I see my density is left and my neutron is right, separating, you can swear this is sandstone. So this means when I look at the neutron density behavior, from the behavior of the neutron density, with my eyes, I can find out the lithology. So when I see my density is on the left and my neutron is on the right, separating, you can swear and stamp this is the sandstone zone. No question asked, because that's exactly what we learned from the limestone scale. When you put everything on limestone scale, sand will separate. Separate in a way where the density is your left and the neutron is your right. When you see that type of separation, just put a stamp with your eyes. This is a sandstone zone. What if they are overlaying? If they are overlaying, it has to be limestone, limestone and limestone. So when I see the two logs are overlaying, put a stamp there. This is a limestone. How about if I see them separating where the neutron is to the left and the density to the right is the opposite of what? Opposite of sand. If you see neutron to the left, density to the right, you have to put a stamp, it's dolomite. So now, even if I put them on the wrong scale, from the behavior of the neutron and the density, I can find my lithology. Okay, I can find my lithology. Okay, so I know my lithology by looking at the behavior of the neutron and the density. And we'll take an example on this because it's very important to understand. So when I see separation between neutron density, my density is to the left and my neutron is to the right, stamp on it, it's a sandstone. When I see him overlaying, put a limestone stamp. When I see him separating like neutron to the left and the density to the right, that's a dolomite stamp. Everybody understand that? This is a very important point. I will say it in a second. But keep in mind, this is the case. All right? Okay. Now, what is the behavior of density in front of clay? Is to go back and look at the clay. We understood the neutron, it will read high because it has lots of hydrogen. How about the other part? See, all the clays, they have metallic component. Metals are heavy. Most, especially if you have iron, for example. Okay, if you have sodium, aluminum, iron, magnesium, all these heavy elements. Heavy elements will make clays heavy. Will make the clays heavy. Let's just go back now. If the clays are heavy, where is the heavy part? This is the 2.95. So this is the heavy area. Okay, this is the heavy area. So my density will be in this heavy area. So now even I understood how the neutron density will react in front of my gamma ray. They will be separated, where my neutron is reading very high and my density is reading high density. Okay, everybody understand that? Why the neutron is reading high porosity? Because of the lots of hydrogen in the clay structure. Why the density of the clay is reading high? Because it have a lot of metallic component that's heavy. So it's heavier in density. So that's why they separate. Now, it raises a question. Okay? Now, I can see that separation which in front of what? Clay? Similar to that separation in front of what? Dolomite. This will make a confusion. So that's not going to make a confusion. So the question here, these two are separated the same. The clay and the dolomite have the same kind of separation. Then neutron to the left, density to the right. Here is neutron to the left, density to the right. Am I in a dilemma? No, I'm not in a dilemma. Because this gamma ray is the most important differentiator. In front of the clays, you have to see high gamma ray. In front of your reservoir, there is no high gamma ray. So when you see that type of separation, look at the gamma ray. Gamma ray will decide. If I see neutron to the left and density to the right, separated, I have to say it's either clay or dolomite. What is the judge? The judge is the gamma ray. If the gamma ray is high, stamp the clay. If the gamma ray is low, because it's a reservoir, stamp the dolomite. Everybody understand that? So the behavior of the neutron density is very, very important to understand. That going back and forth between neutron and density is not haphazard. The neutron and density goes zigzagging and going right and left is not a haphazard behavior. It's a behavior that's understood, and the API put rules for it. The rules is that behavior tells you what the lithology is. Okay? All right. So lithology identification as a summary. Now, high gamma ray, it means clay. Okay? And low gamma ray, it means if density is left and neutron is right, it's sandstone. If density is overlays with the neutron overlay, it's limestone. If then neutron is left and the density is right, it's dolomite. Very simple. Very simple. If it's high gamma ray, it's clay. Okay. Right. Now, here is a very interesting example that we need to follow and identify lithology by our bare eyes. Okay. First of all, my gamma ray here is in red. Here is my gamma ray. And here is my neutron density. And it said identify the lithology. Sorry, this is a wrong mistake. A lithology for the entire log. Now look at this log and how the neutron density are going back and forth. Now use what we learned to identify the lithology here in this log. So you can identify lithology by your bare eyes. Okay. Now, gamma ray, is gamma ray here low or high? Gamma ray is low. So cannot be clay. This is the first thing. Cannot be clay. Look at the neutron density. Are they overlaying or separating? They are overlaying. Then you take this zone and you say, this has to be a limestone zone. No question. So this zone is a limestone zone. So now you trained your eyes. My gamma ray is reading low, so that's a reservoir. That's not a clay. And my neutron and density are overlaying. So this is a limestone zone. because when they overlay, they are limestone. Now, if I look at this zone, what the gamma ray high or low? Gamma ray is high. So you see the neutron is to the left, density to the right, as expected. Neutron left, density right. That happens in front of high gamma ray. It has to happen this way. Okay? If the log is not showing this, something is wrong. Right? So if I have high gamma ray, I have to see neutron to the left, density to the right, separating. Okay. Now, if I go to the next zone, and by the way, this is a well from Egypt. Huh? Here is a zone that's low gamma ray. Low gamma ray. Look at the neutron density. Neutron is still to the left, and density to the right. Now the same separation of clay, but with low gamma ray. Low gamma ray with the neutron left, density right, it's a dolomite. So this zone has to be dolomite. This zone has to be dolomite. Very clear. No ambiguity. Okay? So I know now how to identify where is the clay, where is the lime, where is the dolomite. Let's continue on this. Gamma ray became back high. Gamma ray is high. What's your expectation of neutron density? Neutron has to be left, density has to be right, without even looking at it. When the gamma ray high, neutron is left, density is right. As it has to be this way, and we call this one clay. So clay has high gamma ray. Neutron has to go left, density has to go right. No question, no ambiguity in this. Okay. Now I'm getting to a cleaner zone. It's not very low gamma ray, but it's a clean zone, cleaner. Now, if I look at the neutron density, I can see density left, neutron right, density left, neutron right. That's the sand. Okay, so I say this zone has to be sand, but as you can see, it's a sandstone. Now, if I go to the next one, gamma ray became high. It has to go back to the clay separation. What is the clay separation? Neutron left, density right. You can see that it actually moved from neutron left, density right. Here is the zone. It actually flipped from sand to shale. Very clear, from sand to shale. So this is a shale zone, clay zone. No question. So don't actually think that this zigzagging is nonsense. No, the zigzagging of the log going back and forth, it has a lot of information, and you have to train yourself of how to pick these type of things from the logs. Okay. Now I go to this zone. It's still getting cleaner. It's not very clean. It has some clay in it. But look at the separation. What happened? It actually flipped. Now the density is left, neutron is right. Density left, neutron right, that's a sand. Then this is sand, but we'll call it shaly sand. Sand with some clay in it. Sand with some, why? What did I say with some clay in it? Because the gamma ray is not very low. It's as simple as such. Now, if I go to this one, high gamma ray, it has to go back and flip. Flipping from where? See the upper one? It was density left and neutron right. When it comes to clay, it has to flip. Then neutron left, density right. When the neutron left, density right, it's a clay zone. Now it's coming to very clean zone. Okay? And it flipped again. Here is my density left, neutron right. So this is a very nice sand zone. See? From the zigzagging of the neutron density, I figure out the complex lithology of my reservoir. So the complex lithology, if I follow the rules of the API, then it's so simple to identify lithology by your bare eyes. You don't need any softwares. You have to train yourself on this skill. How to pick my sand zone, how to pick my lime zone, how to pick my dolomite zone, how to get away from the clay zone. That's a skill you have to build by your training your eyes, how the neutron and density are intersecting with each other. Okay, I need to just repeat this again one more time. Make sure you guys understand this. High gamma ray is clay. So don't even waste your time. And you know, neutron left, density right. Okay? Okay. Let me, I'll go back with one more slide. Just one more slide. Make sure that you guys are still following this. Density left, neutron right, it's sand. Overlaying, it's lime. Neutron left, density right is dolomite. Just keep this in your mind. Train yourself, look at so many logs and train yourself on this. But this is the most important part in any reservoir characterization, by visualizing the lithology, by looking at how the neutron and the density are zigzagging together, how they are moving from one side to the other, changing lithology based on your understanding of how the neutron and the density are correlated. Okay? Okay. Now, we understood how to pick the neutron and the density, all right? But you say, well, this is good for lithology. How about my porosity? Because it's nice to know the lithology, but my porosity is actually low and high, low and high. You didn't tell me what the right porosity is, okay? Let me do this exercise with you. You will be surprised, okay? We understood here that the porosity here became 22.5 as a density porosity, and the neutron is reading less for sand. So the neutron is reading less for sand and the density porosity is higher. Neutron and density are overlaying with the same porosity for lime, expected. But also the porosity became high from the neutron and the porosity from the density became low in front of dolomite. You all agree? Say, which one is the right one? Okay. How can I reach this 20 PU? My porosity is 20 PU. It's not 22.5. It's not 16.5. It's not 27.5. It's not 12.5. I say, wait a second. Let's just play this game. Let's just calculate the porosity. On what way? Let's just do this. Calculate the average porosity of neutron and density. Watch it step by step. Let's just understand it. Get the average porosity. What is the porosity here? It's 22.5. What's the porosity here? 16.5. Add them up and divide by 2. You add the density porosity to the neutron porosity and get the average. If I add 16.5 plus 22.5, it gives you 40. Divide by 2 to give you exact 20. So I reached the 20 by taking the average of the neutron and the density? Yes. So what is my actual porosity? Is not the neutron porosity. Is not the density porosity. Is the average of the neutron density porosity. It will give you exact porosity, regardless of your lithology. Everybody understand that? So this is a big value. Let's just do that for the limestone. 20 plus 20 is 40. Divide by 2 gives you 20. So it's exactly like the 20. How about the dolomite? 27.5 plus 12.5 gives you another 40. If you divide by 2 gives you 20. So man, regardless if it's limestone, sandstone, or dolomite, the average porosity is the right porosity. Okay, so that's why the API said, guys, don't worry about it. Calculate, as I told you, put everything on limestone scale. And your porosity is not the limestone, it's not the sand, it's not the neutron porosity, it's not the density porosity. It is the average of the neutron density porosity. So from this limestone scale, we got 2 advantages. From the behavior of the neutron log and the behavior of the density log, I actually predicted my lithology. Plus, from the average of the 2 porosities, I got the exact porosity. So the API were right. Putting things on limestone scale made things much easier. By looking at the log, I can predict the lithology, and from the average of the porosity, I get the actual reservoir porosity. Independent of lithology, it doesn't really matter. If the lithology is limestone or sandstone or dolomite, just average the neutron density porosity, you will get your actual porosity regardless of any lithology you have in your reservoir. So is this a big advantage or not? It's a huge advantage. Okay, and that's why API are not doing this out of being stupid. No, they are not. They know what they are doing. And that's why if you follow what these guys are saying from the API perspective, nothing will be hard. You will be able, by looking at the neutron density, forcing them to be on limestone scale, you got two advantages. The separation will tell you which lithology, and the average will tell you the exact process. So that's a really, really big advantage, okay? Now, so the average neutron density porosity is the exact porosity, not the neutron porosity. Don't read the neutron porosity and say, this is my porosity. This is a mistake. Don't read the density porosity and say, this is my reservoir. No, it's not your reservoir porosity. Your reservoir porosity is the average of the neutron and the density. Okay? So regardless of lithology, doesn't really matter if it's limestone or sandstone or that. We prove this. When we average in front of the lime, it became the same average in front of the sand, became the same average in front of the dolomite. Okay? Yeah. Very important conclusion. So then, don't ever think that the neutron porosity will give you the right porosity. No, it's not. Never ever think that the density porosity alone will give you the right porosity. Your right porosity is the average neutron density porosity. If you work in the industry, we call it sometimes the cross-plot porosity. The cross-plot porosity, that the big word that some people like to use, is actually the average neutron density porosity. So the word cross-plot porosity, sometimes you hear it in the industry, that's the average neutron density porosity, which is the exact porosity of your reservoir, regardless of the lithology that you have. Okay? Let's just go back to this example and try to read the porosity now. Okay? So here is my neutron density overlaying. Here is -15, here is 45. So the distance is 60. Okay? Divided over 10. Then each one of these is about 6. Okay? So what is the porosity here? You say in -15, you add 6, -9. You add 6, gives you -3. You add 6, gives you 3. So the porosity here is 3 pu. Very simple. Don't even worry about it, because this is the average. Now, do I care about this shale? Forget about the shale. No, we are not really producing from the shale. Let's just go to the next one, which is the clean zone that we defined as dolomite. Here is your neutron. Here is your density. Where is your actual porosity? Not the neutron, not the density, the average, right in the middle. To go here with an arrow right in the middle. Here is your porosity. Not the neutron, not the density. It's the middle, the average porosity. And you read the porosity here. So now it will be about 6 pu or so. So this, I'm sorry, 0 pu or so. So this is a 0 pu. Okay, because it's less. Do I care about this one? No, I don't care about this. Is clay. Let's look at this one right here. Where is my actual reservoir porosity? Is it the neutron? No. Is it the density? No. It's in between. What is in between? Here is my porosity in between. Okay. Now here is 15 pu. You add 3 plus. I'm sorry. You add 1.5. No, you add 3. 15 plus 3 gives you about 16 pu. So 15 plus 1 or 2 or whatever gives you 16 pu. So the porosity right in the middle is 16 pu. How about, do I care about the clay? No, I don't care about the clay. How about this one? This one again, what is your actual porosity? Is it the neutron? No. Is it the density? No. What is your actual porosity right in the middle? Right in the middle, if you read it, it will give you 18 pu. Do I care about this zone? No. About this zone, do I care about it? Yes, it's clean and it is sand. Where is my porosity? Is it the neutron? No. Is it the density? No. It's in the middle. You go to the middle and you read your porosity as 21 pu. So here you go. From the neutron density, by my bare eyes, I identified my lithology and I also calculated my porosity. Very straightforward. Very straightforward. Okay? You go right in the middle and you read the scale. Okay? Because that's the middle scale between the neutron and the density. Okay? All right. Now, so we identified lithology, we identified porosity, and we looked at the zigzagging behavior between neutron and density, and we concluded the porosity is not the neutron porosity, the porosity is not the density porosity. My actual reservoir porosity is the average neutron density porosity. Not neither one of them, but the average of both. Okay. Now, for fluid saturation, where does my fluid live? My fluids live in my pore space. Do you know how much porosity you have? We just learned that. I can calculate my porosity very straightforward now by looking at the log. I don't need a software. By looking at the log, I can tell you my porosity is this. Okay, skilled. Don't worry about anybody else using the software. Build your own skills. Okay, I know my porosity by just looking at the log. Okay, I know my lithology by just looking at the log. I don't need the software to help me out. Okay, right. For fluid saturation, now you need to look at the fluid saturation and identify between two things. The one that doesn't have any clay whatsoever, very nice, clean porosity, and the one that has lots of clays inside. Okay, we looked at this also when we talked about the reservoir rock properties and also in the formation evaluation. Here is a very nice zone, pore, doesn't have any clay in it, and here is a pore that has lots of clays. I cannot handle these two the same. Okay, I'll tell you why you cannot handle these two the same. First, Archie is a very well-known saturation model. I calculate my water saturation using Archie. But which one of these Archie will apply? Archie cannot apply on this one that has clays. Archie applies only when there is no clay or very low clay. Let's say 5% clay. Okay? 5% clay is fine, 10% clay is fine. But don't go for 30, 40, 50%. It's not going to work. It will overestimate your water saturation. What's the model? If you look at the model, it actually goes for RW, porosity, and RT. Any mention of here in this equation of any clay, is there anything called clay volume? Is any V clay in here? No. So that's why Archie says, don't even use my model if you have clays, because my model doesn't have any clay information in it. My model assumes your rock has no clay, so my model works only in this one. But it will not work in this case. So when you apply your fluid saturation, okay, make sure you understand your rock. If your clay volume is high, I can put a threshold for you to be safe, according to my experiences in the industry. If you are 10%, if your clay volume is less than 10%, use Archie, you will be okay. If it's more than 10%, don't ever use Archie. Your error will be starting to accumulate and it gets a very high error. So no clay effect is considered, and you cannot actually, Archie works only for clean formation, okay, very low to zero clay content. Now, if you have this law, and now I told you, here are two zones. There is a first zone up here, it has some clay components in there. And this one has very low gamma ray, so it doesn't have much of clay. Now, if I ask you a question, where to apply Archie? Should I apply Archie in this one? No, because you have clay volume here. Okay, your clay volume will be more than 10% for sure. But here you have a very clean formation. So the conclusion is Archie does not work here. Archie actually works here. Okay, so Archie works in this zone, which is the clean zone, and Archie does not work in the shaly zone because it has lots of clay. And Archie equation doesn't have any clay information in there whatsoever. Okay. Right. Let's just take an example on Archie. Let's just say, okay, here is your depth. Calculate water saturation at this depth. Okay. What do you need from Archie? Mr. Archie, what's RW? 0.1. What's AMN? These Archie parameters. We talked about this information evaluation before. I don't think we have to go through this again. But here is my Archie equation. A is 1, M is 2, M is 2 as it's given. RW is 0.1. So I know RW. So I need to know what's my porosity. Did we learn how to get your porosity? Yes, we learned how to get my porosity. Okay. How can I get my porosity in this case? You go to the middle. Well, let's just read our resistivity first. Here's my resistivity reading 40 ohms. Here is my porosity. Where should I put my porosity? Right in the middle between the density and the Newton. Here is my porosity. Okay? Here is my value of porosity 0.15. So I read my porosity in between the neutron density. I read my resistivity from the resistivity log. Then, so I don't have to go and do the calculation. I just put the point here and I read it. It's actually 15 pu. Then you go and calculate your water saturation. It will be about 33%. Let me ask a question. What is that lithology? And I will leave this question and you can guys send it to me by email. What is the lithology in this reservoir? I'm not going to answer that one. I will leave it to you. What is the lithology? By looking at the behavior. Look, your neutron is left and your density is right. Your neutron is left and your density is right. What kind of lithology is this? Looking at the gamma ray. Okay? Think about it and send in an email or whatever, or even put it on the assignment if you want to. Okay? Now, if I have clay, then you have to come up with some other models. You have to have introduced effect of clay on some other models. Clay can be identified by two things, the volume of clay and the conductivity of clay. What do you mean conductivity of clay? Is clay conductive? Well, let's just go back and I remind you with clay conductivity. Doesn't the clay have water? Yes, it does have OH and H2O. Water in our reservoir is conductive because it's salty. Second, doesn't have metallic components, aluminum, sodium, iron, magnesium, all of these? Yes. And these metallic components are conductive or resistive? Metals are conductive. So metals are conductive. Water is conductive. That makes all clays conductive. Okay? So all clays are conductive. The resistivity is low. Why? Because they have both two things. They have water in their structure and they have metallic components in the structure. So between the water and the metallic components, they are conductive. Okay? So these are all that we talked about, all of this. So why clay is conductive? Because water components and the metallic components makes them conductive. Okay? Well, some uses clay volume and clay resistivity and they came up with something like Simondou. Simondou equation tells you, well, here's my water saturation. Why, Mr. Simondou, you are different than Archie? Archie was a very small, nice equation. That Archie doesn't add anything about the clays. Now, here is my V clay, so the clay volume is included. And here is my R clay, clay resistivity is included. So Simondou used the clay volume and the clay resistivity to correct Mr. Archie and get proper water saturation. So now, if you see that you have clay volume, calculate your clay volume, read your clay resistivity, and use Simondou or any other model. There are so many models, by the way. Okay, I like Simondou. It's very straightforward and it's easy to use. So Simondou is a good water saturation model in case you have clay in your reservoir. I really use Simondou all the time. Okay, so Simondou, actually you need to decide your clay volume and need to decide your clay resistivity. Once you do this, you then you go and plug it in here. Very clearly, you can get SW. Actually, I also did this before in the previous lecture. I asked you guys, if you put V clay equals to 0, then Simondou has to take you back to Archie. Because Archie said, I don't have any clays. So this means for Simondou to be correct, this means if I put VC, V clay, in my Simondou equation, this equation has to convert to Archie equation. Okay? And I think I put this in the previous lecture, and many of you actually came up with the proper answer. When you put V clay equals to 0, you actually find that Simondou is exactly Archie equation, because Archie said my model works when the VC equals to 0. Now, going back to the same thing here, so in this zone, I will use Archie. In this zone, I will use Simondou. So Simondou works in this zone because I have clay volume. Archie works in this zone because I don't have any clay volume in this case. So my clay volume will be 0. Then I can use Archie. Or you can actually use for both of them Simando and origin and by itself Simando will convert to Archie because your V clay here is very, very low. Okay, or close to zero. Right? Okay, thank you very much. I said it's enough for today. So we went through so many things, guys. We looked at the behavior of the neutron density. We understood why the API is asking us to put everything on limestone scale. We understood how to come up with the proper porosity, not the neutron porosity, not the density porosity, but it's the average neutron density porosity. Once we come up with what type of lithology do I have, how much porosity do I have, then we go to decide which water saturation should I use, either Archie or non-Archie. I'm not forcing you to use Simando. You can use anything you like. Some people just use other models, depends on how complex the reservoir is. Okay, but for simplicity, go for if you have very low clay volume, like less than 10%, use Archie. If it's more than 10%, use Simando. Simando is a straightforward model that actually uses B clay and R clay straightforward without going into details of clay structure. Because there are some other models like the water model, Waxman Smith's model, Indonesian, and all these. There are so many models that requires more skills that probably you will build up through the days. But at least for the time being, go between Archie and Simando to come up with the proper interpretation. Thank you very much. And I think I have probably like 5-10 minutes for questions, if there are any questions, Mariam.
Yes. So thank you, Doctor, for this informative session. And now we will be addressing the questions. So the first question is that, what is the meaning of PU and porosity?
PU means porosity units. For example, if I tell you you have 20 PU, it means 20% of your rock is porosity. Also, I can write it instead of 20%, I can say 20 over 100, and I can say it's 0.2. So 0.2, we call it decimal. 20, we call it percent. That's what the PU stands for. It's the percent instead of being decimal. So the 0.2 porosity is decimal, which is 20% PU. PU stands for porosity unit. P for porosity, U for unit. Okay.
Okay, thank you, Doctor. So the second question is that, can you please explain the response of different formations to SPE log and shale, sandstone, limestone, and dolomite?
I just did the whole lecture was that, Miriam. I don't know what this question is.
Maybe it is
the whole thing was this question.
Okay, I see. Maybe he wanted something mainly a main difference between the.
Can you just read that he say SP?
Yes, continuous potential log.
This is the second time, even the first time in the first lecture, somebody asked me about SP. There is nothing in the industry now called SP. Nobody is using SP. Believe it or not, SP is a junk tool. Okay? If anybody teaches SP, please ask him to stop doing this. It's a waste of time. Nobody runs SP. SP is a very, very, very old technology. I don't want to swear, but if you go to Halliburton, Schlumberger, Baker, ask for SP, as I said in the previous lecture, they need to go to the junkyard. They have to pick you a tool. There is no tool on the rack called SP anymore. Okay? SP is a very, very, very old technology that nobody is using. If you work in a very old field, like 60s or 70s, you will see SP in the database. If you look at any wells in the 90s, 2000, 2010, even in the 80s, people stopped using SP. It's more problematic than you ever think. Okay? So please, please, please stop mentioning SP. Right? It's a waste of time.
Okay, Doctor, I see. Thank you. And the last question is that, can well log identify the abnormal pressure formation?
Yes, it does. Actually, you can actually use the logging to go for calculating the pore pressure and fracture gradient as well. So you can actually go for the pore pressure gradient and the fracture gradient by looking at the logging data. You can use the resistivity in this or the sonic in this, but that's a very, very long discussion, and it requires a minimum of 2 to 3 lectures to go through this. I teach this in the American University, but that's for the characterization guys. Yes, you do this, and also they do this in the graduation thesis. They also do that, but it will require a lot of preparation, at least to understand how to come up with pore pressure and fracture gradients from the logging. And the two tools, at least two, for whoever is asking this question, the two tools that you need to start with is the resistivity and the sonic. They both are capable of helping you to calculate pore pressure and fracture gradient. Yes.
Okay, so thank you, Doctor, for your time, and hope you guys enjoyed this session. And as a reminder, please don't forget to do the quizzes which are uploaded on the Google Classroom, and otherwise you won't be able to get your certificate. Now, have a nice day and see you in future webinars. Thank you.
Thank you very much. Thank you, guys. Bye-bye.